Hi everyone. In this lesson we're going to be using definitions to write proofs. But as you can see here, the proofs that we're going to write, they are really very short, very simple proofs. We're not really writing proofs. We're just showing how the definitions are going to be used when writing proofs. Because from the next lesson all the way to the end of the unit, we're going to be proving that triangles are congruent. Since on the last lesson we started the unit about congruent triangles, so we need this lesson very important because we need to practice how to use definitions when writing proofs. So it's very important, crucial that you know the definitions. You have to know the definitions in order to be able to do this. If you do not know them, it's impossible to do the proof. So go back, review the definitions that we learned at the beginning of the semester. You need to know all of them. And the instructions for this example says, mark the diagram with the given information, then write the conclusion that follows from the given and a reason that supports your conclusion. So you have to mark the diagram, very important. So you show that you really understand what's going on with this information that is given, that you understand what happens from the information that is given to you. You should be able to get some conclusion from the given, and that conclusion should be marked on the diagram. And then, of course, you have to support, as with any proof. Remember, the proofs have two columns. One column, the one on the left side are the statements, and the one on the right side are the reasons. And for every statement that you write, you have to provide a reason. So you have to write the reason that supports your conclusion. So in this case, the first one, called 8, it says given D is the midpoint of AC. So in this case, the definition that we want to know, that you need to know in order to be able to get a conclusion, is the definition of a midpoint. What is a midpoint? What does a midpoint do? And the definition of a midpoint is this. A midpoint of a segment is the point that divides a segment into two congruent segments. So if you have a midpoint, such as, let's say this, then that midpoint will divide the segment into two equal parts. And these are the marks that we need to show that we have two equal parts as a result. So if you read here carefully, it says D is the midpoint of AC. So we're on our diagram, D is right here. And that D is the midpoint of segment AC. So we're dealing with this segment here. The other segments have nothing to do with this problem. D is the midpoint of segment AC. So D must divide segment AC into two equal parts, which are obviously this part, which should be congruent to this part. So those are the two equal parts. That would be what we get from this point being the midpoint. That's the conclusion that we get from our given. So if the first statement would say here, D is the midpoint of AC, and that's a given. The second one would be the result that we get from that given, which is the fact that AD, segment AD, is congruent to segment CD. And why do we say that? We say that because that is what the definition of the midpoint says. It says that a midpoint divides a segment into two equal segments. So I'm supporting my statement number 2 with the definition of the midpoint. So that's my reason for writing that statement number 2 is the definition of midpoint. And we're done with this. We're just writing an example of how we will use the definition of the midpoint when writing a proof. Don't forget to mark the diagram, write the conclusion that you get from the given, and the reason. Also, whenever you're writing segments, always try to name the segments based on the correspondence. So AD, I'm starting from this vertex going to the middle of the segment, sort of. So the first letter here would be what corresponds to A, and what corresponds to A would be C. So that's why I start by naming C and then going to D. It would be the same thing to say DC, but we always try to name it according to the correspondence, and that's why I put CD. Let me rewrite this because this doesn't look clear. So this is going to be CD. Okay. So next one, B. In this case, the given says BD bisects AC. So we're dealing here with a bisector. And we're looking at what type of bisector we have, because you could have an angle bisector or you could have a segment bisector. And if you read carefully, it says BD bisects AC. So this AC, this is the thing that is being bisected. This is the thing that is being cut into two equal parts, because remember that that is the definition of a bisector. If we're talking about bisecting a segment, as in this case, we're bisecting segment AC, we are talking about cutting the segment into two equal parts. So we are dealing with a segment bisector, and the definition says that the bisector of a segment is another segment or a line or a ray that divides the segment into two equal parts because it's passing through the midpoint of, in this case, segment AC. So remember also then that a bisector for a segment would act in the same way as the midpoint because it passes through the midpoint. So I come to my diagram and BD bisects AC. So our segment BD, that is the bisector, that is what is cutting the other one, and the other one that is being cut is AC. So very similar to number 1 or the first one on the top. AC is divided into two equal parts because BD is the bisector, and so D would be one more time the midpoint because a bisector passes through the midpoint. So in this case, we have already number 1 filled out. BD, segment BD bisects segment AC, that's given. What we get from that? We get that we have two equal parts because that is what a bisector does, and those two equal parts are AD congruent to CD. And why am I saying this? Is because I have a bisector. So I'm supporting my statement number 2 with the definition of a segment bisector. And so I have everything that I need. I have my diagram marked. I have the conclusion that I get from the given and the reason to justify my conclusion. C, given segment BD bisects angle ABC. So that is our given. We're again given a bisector, but in this case, it's a bisector of this angle here. It's not a segment bisector, it's an angle bisector. But again, a bisector divides something into two equal parts. So in this case, this angle is going to be divided into two equal parts. So let's look at the angle in the diagram. That is here, angle ABC. Remember that you have to follow the name of the angle to form the angle on the diagram. So ABC, this is the angle that is being bisected or cut into two equal parts. That angle that we see over there. So that means if that is the one that is cut into two equal parts by segment BD, which is the bisector, so the two parts that are equal, which are going to be angles in this case, are going to be the parts that I'm marking right now. This angle is going to be equal to this angle. If we're bisecting an angle, the result should be angles. So BD is the bisector of angle ABC. The two angles that we get that are congruent, it's angle ABD and angle CBD. So the first statement is already written. BD bisects angle ABC, and that's given. The result from this is that angle ABD is congruent to angle CBD. Again, I'm writing based on the correspondence. What corresponds to A, which is C, goes first. What corresponds to B, which is B also. And what corresponds to D, which is also D. And I'm saying this because I'm using the definition of an angle bisector. So definition of angle bisector. And so I have everything that I need. I have the diagram marked, the conclusion, and the reason to support the conclusion. The next one, D, says given BD is perpendicular to AC. So remember that the symbol that we see here is perpendicular. And perpendicular, what does the definition of perpendicular means? Or what is it? Remember that perpendicular lines are lines that intersect to form right angles. So that's the definition of perpendicular lines. Perpendicular lines are lines that intersect to form right angles. So when these two lines intersect, you should be getting right angles. So look at where are they intersecting. That is where the two right angles should be, or 3 or 4, depending on how the diagram looks. So BD intersects with AC right here. So that's where the two right angles are going to be formed. In this case, 2, because we don't have anything at the bottom, it's going to be 2 right angles. So this is going to be a right angle, and this is going to be a right angle, because that is what the definition of perpendicular line says. It says that you get right angles from perpendicular lines. So I already have the first statement. BD, segment BD is perpendicular to segment AC, that's given. what do I get? I get that angle BDA is a right angle. And how do I know that? Is because that is what the definition of perpendicular line says. Okay, and of course the other angle is angle BDC, and I'm going to put that on the next line. You could actually put these two in one, but I'm going to put here in two. So angle BDC is a right angle. And for the same reason, definition of perpendicular lines. So again, we could have put this into one statement since it's the same statement and we have the same reason for both of them, but here we are writing into two separate statements. So I have everything that I need. I have my diagram marked with the right angles. I have the conclusion that comes from our given, or the conclusions in this case, and I have the reasons to justify. Be careful with perpendicular lines. Some people are usually tempted to say that you have 90-degree angles, but if you are very careful with the definition of perpendicular lines, the definition of perpendicular lines does not mention a 90-degree angle. Yes, we know that right angles have 90 degrees, but that is not part of the definition of perpendicular lines. So perpendicular lines that intersect to form right angles. We follow the definition precisely, and so the result or the conclusion should be that we have right angles, not angles whose measures are 90 degrees, although that will be true, but that is not coming directly from the definition of perpendicular lines. Okay, so next one, I'm just going to give a very simple proof, but I'm also going to introduce a very important theorem that we're going to be using a lot, which is here written on the top. The theorem is this one. All right angles are congruent. So this is a new theorem that I'm adding today. All right angles are congruent, and that's obviously true because all of them measure 90 degrees, and congruent means having the same measure. If you have two right angles, they are obviously congruent. So we're just saying that in a theorem, or that's a theorem that we have about right angles. All right angles are congruent. So I'm going to just show you how we would use that here. We have a given which says BD is perpendicular to AC at D, very similar to the last one. And our job is to prove that angle BDA is congruent to angle BDC. So we want to show that these two angles are equal. We don't know right now that they are equal. It is our job to show that they are equal. So what we have, what's the information that we have to start our proof? We have that BD is perpendicular to AC. So what can we get from that? From this given, we can get that we have right angles because that is what the definition of perpendicular line says. It says that we get right angles. So I'm going to show that here. Well, I know so far that where these two lines intersect, or where these two segments intersect, BD and AC, that's where we're going to have right angles. Okay, so we have right angles. And then we have our theorem that says that all right angles are congruent. So because they are right angles, the next thing that we're going to say is because they are right angles, they're congruent. And that's it. That's how we finish this one. So we only have 3 statements and 3 reasons. So basically, I have planned the proof mentally. I haven't written any plan. I'm just doing it mentally, and now I'm going to be writing the proof. So this is how we usually do. We plan mentally, and then we write the proof. But you should already know what you're going to be writing because you already planned mentally. So this is what we have. How do we start? We start with this. So BD is perpendicular to AC at D. So that means D is where they intersect, and that's given. Then what happens at the point of intersection? We get right angles. That is what we get from number 1. We get that angle BDA and angle BDC are right angles. I'm going to put all that in one statement here. Angle BDA and angle BDC are right angles. And that is because of the definition of perpendicular lines. We usually should have the definition on the previous statement. So we're using that definition in order to get number 2. So that will be our reason, the definition of perpendicular lines. And now we have a theorem that says that all right angles are congruent. Therefore, because these 2 are right angles, we could say now that they are congruent because we have a theorem that allows us to write that. So we could write that angle BDA is congruent to angle BDC, and that is because there is a theorem that says that. There is a theorem that says that all right angles are congruent. So I'm writing here the theorem itself. I'm not sure. I don't think the theorem has a name, so we cannot really call a name or just put a name over here. We write the theorem itself. All right angles are congruent. That's our reason for writing step number 3. And so that is how we would use definitions, and in this case, a theorem. In writing the proofs, I need you to practice. Please go back and review all the definitions, all the theorems that we have learned up to this point, and do the homework so you are ready for the rest of the unit, which is writing proofs about congruent triangles. So please study the definitions so you are ready for the proofs. And that's it for the lesson of today on how to use definitions when writing proofs.